All right, 2.8, inverse and inverse trig functions. We're going to start with inverse functions and then transition into the inverses of the inversest of all inverse functions, the inverse trig functions, okay? So remember what an inverse function does. It's something in mathematics that we really can't do sometimes in life, like taking things back, right? Like when I went home and told my wife about my crazy idea to have students select my facial hair pattern, she says, no, call it off. You can't do that. I'm like, the toothpaste is out of the tube, honey, right? Can't do that. So I can't take that back. And I don't want to take it back, okay? With my ugly look, whatever, my wife will have to take me back. So in mathematics, though, we can undo something. Sometimes we can undo something. And that's what an inverse function does, right? So like if you multiply by 5 and you're like, oops, didn't mean to do that. How do we undo multiplying by 5? Divide by 5. So multiplication and division are inverse operations, right? If I add 3, oops, subtract 3, right? If I square something, oops, square root it. Now, does that always work? No, okay? Because if I told you that I squared something and got 36 and oops, I didn't mean to, y'all wouldn't know what I started with, right? So not every math function has an inverse. That could have been 6 or -6, okay? But we can sometimes help out functions that don't have inverse functions if we restrict the original domain. Like if I said, hey, I'm thinking of a negative number only, and I squared it to get 36. Now y'all could say, oh, your original number must have been -6, right? Good. Or if I squared a number and got 49 and it was a positive number, 7. Yeah, 7. Good. Y'all are good with y'all's multiplication. See, so we denote the F inverse like this. It's a really cumbersome notation. We don't read that as the reciprocal of F, okay? That is reserved for inverse notation. But you got to be careful, because if we write F squared of X, that means F of X quantity squared, okay? But this does not equal F of X to the -1st. It does not, because that equals 1 over F of X. So that's why we have to just give this like superior status. We read that as F inverse of X. It's not the reciprocal of F. Now, it's real easy to tell if a function is going to have an inverse that is also a function, right? If you think about what I said about squaring a number, think about the graph of X squared. Here's Y equals X squared, or F of X equals X squared. If the original function passes the horizontal line test, then we know its inverse is going to be a function, right? The horizontal line test. To be a function, it has to pass the vertical line test, right? But that just means that each input can have no more than one output. If we wanted to have an inverse that is also a function, then I need my inverse to pass the vertical line test, the graph of it, okay? But you could do that test on the original function by doing what's called the horizontal line test. So X squared, as you notice, touches this horizontal line twice everywhere except the origin. So it fails the horizontal line test. So its inverse is not a function. But if I do this, if I say, you know what, we're working with just positive values of X, like this. If I say X is greater than or equal to 0, now does that piece pass the horizontal line test? Yeah, now that passes the horizontal line test. And what would its inverse be? Its inverse would be this. F inverse would be what? How do you undo squaring something? Take the square root of it, okay? So that's true with all inverses. All right, you can make exceptions for functions that aren't automatically inverses of each other. All right, now, what do Minnie and Mickey have to do with this? Any function that passes both the vertical and the horizontal line test on their own without us restricting the domain, we say are 1-to-1, okay? That just means for every X, there's only one Y, and for every Y, there's only one X. That's the difference. For functions, for any X, there's only one Y at most. But like for X squared, there were 2 Ys that, or that one Y had 2 different X values. That's not good, okay? So Minnie and Mickey are 1-to-1, because for every Minnie, there's only one Mickey. And for every Mickey, there's only one Minnie. 1-to-oneness is a very romantic idea, right? For every x, there's only one y, and for every y, there's only one x. That makes inverse functions useful for like coding information, right? The earliest messages were sent under code or cipher. You can cipher or code your message in a particular way so that the person on the other end could decode it only one way, right? You wouldn't want them to be able to decode it multiple ways because then your message, can get misinterpreted. So functions make really, really good coding sequences. In fact, public key cryptography is the study of how mathematics makes e-commerce safe, right? Like every time you order something on Amazon, your information is being transferred over to the account, and there's some mathematical equation that's being applied to it. And then the person on the other end has the key, and it's 1-to-1, right? So like when you pay $50 for like a costume for the pep rally, they don't read it on the other side. Like, this guy just spent $700 on this costume. It's like, no, only 50. I don't know yet if this Friday is supposed to be USA Day or Space Day. It was originally supposed to be space, right? It is space. Okay, officially. Yeah. Yeah, because we're honoring a lot of the veterans. That's why I asked, we're honoring veterans at the pep rally, and we're honoring veterans at the football game. So
probably be USA then.
Well, I just talked to one of the cheerleaders and they said it was space/Save Britney or Free Britney.
Yeah, that's fine. I emailed Coach Dozier and Coach Malone. I haven't heard back, but yeah, it was originally supposed to be space. Okay, back to Minnie and Mickey. I'm sorry, I got off task there. So if a function is 1-to-1, we call that function invertible. Okay, that's just by definition. An invertible function is 1-to-1. A 1-to-1 function is invertible. That just means you can undo it. There's a function for undoing it. Okay. Now, let's go ahead and write real quickly using non-calculus the inverses of these functions. You can represent a function by a set of ordered pairs. So first of all, we know it's a function because there's no repeated x values. Okay. So what would be the inverse function? Well, let's write it. F inverse colon. If the original function turned a 2 into a 5, what would the inverse function do? It would take a 5 and turn it back into a 2. Okay. So notice what we do there is we just interchange the x and y. Yeah. That's why when you were taught to find inverses in algebra 2, you were told to switch x and y and then resolve for y. Because in the process of resolving for y, you're doing the inverse operation in the reverse order. If I took a number and added 1 first and then multiplied by 3, the first thing you would do to decode it would be divide by 3 and then subtract 1, right? Inverse operation in the reverse order. That's what solving for y once you switch does. So this becomes then 6, 3, 2, negative 1. You get the idea. 7, 4. Now, before I walk away, let's see if this function f is actually invertible. Is f inverse a function? Its inputs now are 5, 6, 2, and 7, and those are all unique. So yes, so we would say that this function is invertible. It is a 1-to-1 function, and f and f inverse are inverses of each other. They don't fight over who the inverse is, right? We use f inverse notation, but believe it or not, what's the inverse of f inverse? F, right? So if you have a sibling, you don't go home and argue over who the sibling is. I'm the sibling. No, I'm the sibling. Well, you can't be the sibling because I was here first. Same thing with f and f inverse. F might have been there first, but f inverse, okay? All right, letter B, f of x equals 5x minus 8. So you could do this one intuitively, right? Let's go ahead and change f of x to y. If I pick a number and I multiply it by 5 and then subtract 8 and give you that result, all you would have to do to get back out of it would be to take my input that I give you and do what first? Well, let me see. I'm thinking of a number. I multiply it by 5 and I subtract 8. What number was I thinking of? What would you do first? You would add 8 because the last thing I did was subtract 8. And if the first thing I did was multiply by 5, the last thing you would do is divide by 5. Okay, so you could do it intuitively like that. But sometimes intuition is not enough. So that's why we have the algebraic technique. Interchange x and y and then use your algebra skills to find it. Let's see if we get the same answer. In my quest to solve, I need to switch x and y. So let's move this down. And here's the money step. I'll call it cha-ching colon. Okay, and I'll even do it in green. X equals 5y minus 8. That's the money step, right? Because we interchange x and y, and then all we do is resolve. So for y, so we get x plus 8 equals 5y. Divide both sides by y, and we get x plus 8 all over 5. And lo and behold, now that we have it, we can call it f inverse. Now, let's look at another version of this inverse function. The way we have it is really nice, but we can divide both of them by 5. That's the same as 1/5 x plus 8/5. Yeah, yeah. And that's the graph of a what? Mx plus b, that would be a line, right? A slanted line. So look, 5x minus 8 is a line, right? -8 is the y-intercept, up 5, right 1, up 5, y 1. That would pass the horizontal line test. A line, slanted line, passes the horizontal line test. So it's automatically going to have an inverse. Turns out the inverse is another line, right? With a slope of 1/5. What do you notice about the relation between the original function's slope and the inverse function slope? Reciprocal of each other. Is that a coincidence? Maybe, maybe not, right? Maybe, maybe not. To know if it's a coincidence or not, all you got to do is change 5 to like a variable, work through it, and if you end up with 1 over a, then you know it's not a coincidence, right? That's a real easy way to test that theory. And it turns out that if you did replace 5 with a, you will always get 1 over a as the inverse slope. So let's make this connection right now. Eugene is a great barber. Eunice is even better barber because women are better than guys at everything.
Yeah.
Trust me, guys, it's true. Okay.
I got these hands.
No, here's what I want to reinforce. These two lines are inverses of each other, and they have slopes that are related how? They're reciprocals of each other. Yeah. Inverse functions always have reciprocal slopes. Always. Okay. Inverse functions of lines that are single slopes always have reciprocal slopes. Okay. So let's look at letter C. Here's another way to represent a function. This function passes the vertical line test. Yes, yes? Is it 1-to-1? Is it invertible?
It sure is.
How do we tell? Horizontal line test, right? So it is 1-to-1. Now, if you wanted to graph what the inverse looks like, you could do it step by step. Let's call this point down here -5, -3. So -5, -3, if you switch it down, would be -3, -5. I'm just using the blue points from left to right. The next blue point would be at -3, -2. Flip those around, you get -2, -3. The next blue point is at -1, 0. Flip it around, you get 0, -1. The next point's at 1, 1. Flip it around, and you get 1, 1. The next point is at 3, 2. Flip it around, you get 2, 3. And then the last point looks to be at 5, 4. Flip it around, you get 4, 5. Now, if we connect those dots, you get something that looks like this. And that passes the vertical line test. So now we'll call that F inverse. Do you notice any symmetry between these two guys?
Yeah.
There is, right? Would there be a way to graph an inverse graph of a function without doing it point by point based upon this? There should be. Turn your head at a 45-degree angle to the right. Now, do you see any symmetry? Or tilt your iPad 45 degrees to the left. All of those with bad necks and cleverness. Yeah, it appears to be reflected across the magical line that is known as y equals x. Snap. There it is. Snap. It is. It's a reflection across the line y equals x. That is money. Okay. And that's true for all inverses. If you reflect a graph across the line y equals x, you get the graph of the inverse. So it's real easy to tell if a function, a function that it doesn't pass the horizontal line test fails the vertical line test, because guess what happens to the x and y axis when you reflect them across the line y equals x? They become the y and x axis. A vertical line becomes a horizontal line, and a horizontal line becomes a vertical line when you reflect it across the line y equals x. Now, when you get back from lunch, we'll ask the question, why the line y equals x? Why should that work? Something to think about. Food for thought.